Hi, welcome to lesson 3. Today we are going to learn how to write a complete Navier-Stokes solver, and we will show this on an example of a laminar flow with simulation of a Magnus effect. For those of you who do not know what Magnus effect is, you certainly know that once you kick a ball and it starts spinning, it will go to one of the sides. So the phenomenon, which is well known, when the flow comes from one direction and the body is moving around, is spinning, then there is a force exerted on this body by the fluid. A very nice application, you might not be fully conscious of that, but there are, for example, ships which have spinning cylinders, and when the wind is blowing from one direction, it generates lift, so to say, a thrust. We will try to simulate this effect in a laminar flow. So please let me assume that we've got a rectangular geometry. We have to separate some portion of the fluid, and we will be assuming that the fluid along this and that boundary can travel along this tangentially with no viscous forces and no viscous stress. We have the inlet, we've got the outlet, and we've got our rotating cylinder. So let's go to the MATLAB script. As previously, first we are clearing the workspace and the command window, and as recently we have prepared a mesh for you, so you can download the Magnus MSH file, and we import our mesh with import mesh gmesh function, and it stores our mesh to PE and T arrays. We can display it mesh. Let me show you our mesh. So this is the mesh that we will be working on. It is finer in the area of the cylinder and a bit finer in the area of the wake upstream of the cylinder. It does not need to be that fine for a stable simulation. Here comes a bit of theory, where first all defined elements do not work well for incompressible flows. So without going deep into theory, please simply remember that we always need to convert mesh to second order if we want to simulate the flow, the incompressible flow. So we simply make a call to this function. It generates again PE and T arrays, which store the mesh, but at this moment the mesh is not, we haven't got first order defined elements, but we've got second order defined elements in our mesh. Additionally, we get information about number of velocity nodes in the mesh, number of pressure nodes, because the pressure nodes are those of the original mesh. The velocity nodes are, let me show it once again. Well, so pressure nodes will be all the nodes that you see. These are the original nodes, and the velocity nodes are with the convert mesh to second order function. There are additional nodes which are put here, 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 so to say in the middle of each of the edges. So by doing this, the second order mesh is created. So you basically have got more velocity nodes in your mesh than pressure nodes. And the indices is a special structure which helps to easily refer to u velocity field, I mean x velocity field, and y velocity field, and pressure values. Then we define fluid viscosity, because we will be working with circular cylinder of unit diameter, and we will have unit inlet velocity. Basically, this viscosity means that we will work on Reynolds number equal to 100. So certainly a laminar flow, and we will get a steady state solution. You might experience oscillatory solution and some problems with convergence if you go to high Reynolds numbers, because then basically the physics looks like that you haven't got any stable solution to the flow around the circular cylinder. All right, so we defined the new kinematic viscosity, and what we do, we will be working on, we will have an iterative procedure to iterate our Navier-Stokes equations. So we need to have an initial gas, so we init our solution with unit velocity in the x direction, 0 velocity in the y direction, and 0 pressure values everywhere. We need to set certain convergence criteria for our iterative process. Basically, we need to iterate because Navier-Stokes equations are nonlinear, so we need to solve for the nonlinearity. Maximum residual value that we can accept will be 1 to the power of -3, and at the same time we limit number of iterations to 25, so to say, well, even if we had problems with convergence, we do not want to make more than 25 iterations, and at this moment the simulation would stop even without convergence. But of course, if you can reach 1 to the power of -3 earlier, then the simulation will be finished before making 25 iterations. All right. We want to specify velocity, inlet velocity. Inlet velocity would be 1 in the x direction, 0 in the y direction, but this is nothing more than simply the boundary condition on the inlet boundary. These two lines I will address in a moment because they are not needed in usual simulations with non-rotating walls. We will only need it for the simulation of our Magnus effect. So let me come back to that in a moment. For a standard Navier-Stokes solver, we right now start the iteration loop. So as you can see, we start a for loop which does a certain number of iterations. And again, the idea of the toolbox is that you have to assemble proper system of equations that represents the problem that you want to solve. So for Navier-Stokes flow, we assemble Navier-Stokes matrix to the P, E, and T information about our mesh, new kinematic viscosity, U. This will be the solution vector, which will be storing the whole solution to the velocity field and the pressure field. And the nice thing about the indices structure is that you use this indices.ind_u to refer to u velocities, I mean x velocities, and you use u at indices.ind_v to refer to y velocity values. And you basically have got two options. You can use a stabilized formulation with stabilized finite elements with SUPG doubly asymptotic flag, or you can specify no SUPG if you want to use non-stabilized finite element discretization. This function generates you Navier-Stokes matrix and right-hand side vector. And again, as exactly in the same way as in our previous lesson, we need to impose boundary conditions. So we use a slightly different function. This time this will be impose CFD boundary condition to D, PET, mesh, matrix, right hand side, and we tell at physical line number 10 we want to tell this will be our inlet with unit velocity in the x direction and 0 velocity in the y direction. Because we have defined this vector here, you can also write simply val. This will be even more clear. For our case, we want to mimic that our domain extends much further to the top and to the bottom, so this line and that line won't be walls. This is just some kind of imaginary wall where we need to limit our domain. So we would apply slip along x. This is a boundary condition which tells there is no flow across the boundary, but the fluid can slide, can be sliding along this axis without any viscous forces. So at lines denoted by 12, because you can see 12 is both here and here. Along these two lines we specify slip along x boundary condition, and the last boundary condition that we need to specify is our rotating wall. Again, mesh, matrix and right hand side that will be modified during imposing of boundary conditions. Our cylinder is denoted by physical line number 13, and we specify rotating wall boundary condition, and this boundary condition needs information about an axis where the rotation axis is placed, and the second information about the angular velocity at which the body is spinning. So you need to specify a structure which is consisting of two fields, axis, where in our case it is the axis is located at x equals 0, y equals 0, and you need to specify angular velocity, which is 5 radian per second. The nice thing, if you'd like to simulate the flow around a cylinder, around one which is not spinning, let me comment out this, and this boundary condition would be called simply wall and does not need any additional parameters, and that's it. You can try one of the second option, but we are interested in the Magnus effect right now, so let's move back to the original version. Compute and plot residuals. You would like to have some control to see whether your solution converges or not. So you've got a special function, compute residuals, which takes always the same arguments. You don't need to bother much. I never bother about these arguments. I simply copy and paste this. This is standard. Then plot residuals to see how it converges, to see whether the residuals drop and your simulation goes well, or whether you have some problems with convergence and the residuals oscillate or even diverge. Then the simple stop criteria. If it has converged, then simply break the iterations. And the last thing in every iteration is solution to the linear system of equations. Once it is solved, we go back, and the new once again the Navier-Stokes matrix is assembled. But please see that right now you've got updated x velocity and updated y velocity, so that's why it is a better approximation to the correct Navier-Stokes matrix, and that's why our process converges. At the end, we want to plot our solution. In figure 3, we display x velocity. As you can see, u at indices.indu means x velocity. Because pressure, you remember from my comment at the beginning of our lesson, because pressure is represented on first order grid. This is actually nice to generate pressure data everywhere. Everywhere means for all velocity nodes, and then we can display solution. We can display pressure values which are at this moment are stored everywhere in the mesh. So if you want to display pressure, this is a nice way to do it. Probably not the only one, but it's nice to remember about doing this. Well, you might be bothered, where did we specify fluid density? Well, we didn't, because we are dealing with an incompressible flow, so you can divide your Navier-Stokes equations by density, and the only difference is that the pressure you get from the simulation is pressure divided by density. So if you would like to have real pressure in pascals, you should multiply this pressure by the density of the fluid you deal with. Alright, let me run the simulation right now. It converges pretty quickly. Remember, we've got angular velocity of 5 radians per second. So what you can see on the x velocity field, we've got angular velocity equals 5. This means the cylinder is spinning in this direction, and clearly you see negative velocities here and positive velocities here, and you see a non-symmetry in the pressure distribution, and obviously these low pressure values here mean that you will have a negative lift force which points downwards, and this is the Magnus effect that we wanted to simulate. To measure that force, you can always go to our script and say that you would like to compute the force. We are doing this by the following. Force equals, we've got a special function, compute force, and let's say what the arguments should be. P, E, and T, this is the mesh. U is the whole solution vector. Kinematic viscosity and wall IDs. We want to measure force on the cylinder, which is denoted by physical ID number 13. With F9 button you can run this single line. Alright, if I don't give a semicolon, we will see that we've got some drag force, but we've got negative lift force. Now let's see what happens if we change the angular velocity. This is really what is interesting in the Magnus effect. If we would be rotating this quicker, we can simulate once again. We've got higher velocities at the cylinder, so the convergence process goes a bit longer. With increasing Reynolds number, there are bigger problems with convergence. Basically, it comes from the physics. If you deal with a physically unsteady flow, you should simulate with unsteady settings, or you should simulate it with turbulence models if you deal with a turbulent flow. Of course, laminar flows for high Reynolds numbers do not exist. All right, x velocity field, pressure field, but let's compute the force again. You can see previously we had more or less -3, right now we've got -4.8. And if the cylinder is not spinning at all, then we've got fully symmetric pressure distribution and velocity distribution, and what you can see is that, well, we've got a very small lift force. Basically, this is due to some numerical errors, and surely you also should notice that we are converging our solution only to residue of 10 to the power -3, so there can be small discrepancies coming from the numerics. Thank you for the third lesson, and see you again in the heat transfer problem, which will be presented in the next lesson.